Hello, and welcome to the AI Engineering Podcast, your guide to the fast-moving world of building scalable and maintainable AI systems. Your host is Tobias Macy, and today I'm interviewing Anush Elangovan about AMD's work to expand the playing field for AI training and inference. So, Anush, can you start by introducing yourself?
Hey Tobias, this is Anush. I lead the software team at AMD and for GPU software. Excited to be here.
And do you remember how you first got started working in ML and AI?
It was about 10 years ago, actually more than 10 years ago. We were building smart devices for IoT, and we were building technology that, it was the early days of ImageNet and things like that, right? Like, so we were trying to do gesture recognition with the early AI concepts. And then one thing led to another, and we started building ML compilers about 7 years ago. And then about 2 years ago, AMD saw the work we were doing in ML compilers and how we were able to target any ML workloads on any AI accelerator. And they acquired Nod.ai, which I had founded with a strong team. And we became a core part of the AMD software strategy.
And so, in terms of your work at AMD, obviously you're very focused on the software layer, but for a very hardware focused company, I'm wondering what are the elements of that strategy and how they factor into the competitive advantage that you're able to gain by virtue of focusing on the software elements of a very hardware focused problem.
Yeah, I think AMD has traditionally, done a very good job with hardware. They have a pervasive AI strategy that goes from embedded laptops, gaming PCs, all the way to the data center. And they have a very good cadence of execution of this hardware, right? Like they're just like very relentless in building good hardware. And about 2, 3 years ago, when the AI boom was taken off, there was a focus to bring all of that hardware together with a software strategy that allowed for like a software platform to be built on top of all of this great hardware innovation. And so that's part of what our team does, which is build out software and ship software like a software company, but be part of the AMD like innovation engine that builds all of this awesome hardware. So when you pair that awesome hardware with great software, then it really unlocks great business value for customers, and more importantly, it moves the industry forward with respect to the ecosystem it enables, because AMD provides a very open environment for collaboration, and all our source code and software is open source, which allows for innovation to go at the pace at which the people using our practitioners want to, right? And it's not limited by the ability of what we put out in closed source form.
And on the hardware side of the AI ecosystem, obviously the competitive landscape has been largely dominated, at least in terms of marketing, by NVIDIA. The CUDA ecosystem has become an entrenched player and gained a lot of adoption because of the fact that it was one of the early movers in the space for numeric computation, which was largely focused on scientific computing, and then got parlayed into its current position in the AI landscape. And I'm wondering what you see as the current state of affairs as far as where the attention is going versus the realities as far as the actual capabilities that are provided both at the hardware and in the software layers that are built on top of that. So thinking in terms of the competitive advantages between what CUDA has and its relation to NVIDIA hardware and the work that you're doing at AMD with the ROCm stack.
Very good questions. And just the first way I'd answer that is capability wise and performance wise, we are on par or better. And the data to back that up is we run like 1 million or two models from Hugging Face every night to make sure that all the models run out of the box, without any problems on AMD hardware. So that's kind of like a thing, right? And then every model that has been released in the last year, like Llama 3, Llama 4, DeepSeek, Qwen 3, everything worked out of the box with whatever ROCm version we were shipping at the time. And more importantly, it was performant. So right now, if you go look for like what is the best way to serve DeepSeek, which is the most popular open source model, it is on MI300 with ROCm, right? That is, just performance. Not even no TCO advantages, nothing else, right? Just performance wise, it's better than what NVIDIA provides. And so maturity wise, I think we're at a point where it's good. But there is also the perception part and kind of like like you said, the entrenched ecosystem part, right? So if you look back in history, you can always kind of think of similar transitions in technology, right? There was like Nokia and Symbian, right? Like that was like 98%. There was no way that anyone's going to get anything else, right? And it was a closed source operating system. It was obviously there was a inflection point of like, when smartphones came out, and then we had the iPhone and we had Android, and it just kind of like overnight it took over. But I wouldn't necessarily just say it's exactly like that, but it's a process that once people realize that, hey, this just works, it clicks, and you're like, oh, why would I be doing something in a closed ecosystem? Why would I be paying more for less performance, right? Those are all like factors that it just connects, and then it's a snowball effect of like, okay, now we just deploy with AMD, right? And AMD has been through this journey with CPUs. In 2017, I think 2017, 2018, it was like 2% of the market share in data center CPU. Right now, it's like it's almost, I'd say, I depending on what's out there right now, it's almost half the market shares like with us. But that was a journey too, right? At that time, with 98% market share, the incumbent was, like there was no way that anything could change. We think, or I personally think, the transition and the adoption in GPUs and AI software will be a lot faster than what you'd see in CPUs, because AI is just about speed. It's about how fast you can move, how fast you can deploy, how fast you get the value for what you're using, and how fast the next technology shows up, and whatever you deployed is no longer useful, right? So you need the ability to move fast, and that velocity gives you the ability to iterate faster. And if we focus on our execution, it's ours to take.
And then another piece of that puzzle is the communication between the CPU and the GPU, and some of the amount of offload that you're able to get onto the GPU, as well as the level of efficiency that you're able to get for CPU compute for some of the less parallelizable elements of the model inference and model training. And I'm wondering, what are some of the ways that the work that you're doing at ROCm works to optimize some of that communication and offload from CPU to GPU, given that you're able to work both on the CPU and the GPU, given that it's all from the same manufacturer, versus the situation with Intel and NVIDIA chips, where they're two different manufacturers, and so it requires more organizational communication.
That's a very good question. The good thing, like philosophically, even though the silicon is from AMD, right? The CPU can be an AMD CPU, the GPU can be an AMD GPU. Networking can also be from AMD, right? We make what we call AI NICs. But the standards in which we connect them are open, right? Like AMD is part of the UA Link standard, the UEC consortium, the Ultra Ethernet consortium. So we want to make sure that we have the ability to build a reference that has all of these like cool integrations, but also if someone were to build something better, they should be able to drop into that ecosystem and unlock the ecosystem. Unlike in the competitor space where it's like, hey, this is InfiniBand and only we do this, or you can you have to play by these rules, right? So that's one, which is the ecosystem aspect of it. The second part of what you asked was important, because having the ability to build the CPU, which we've built multiple generations of, and GPUs now, it's intensely popular. It gives us the insight into both CPU workloads, GPU workloads, and at what point do we transition from CPU to GPU. There's increasingly more focus on test time compute, things like, where you want to do some sort of post inference, or like the thinking models that are out there now, right? That allows for a a new kind of scaling. And we are very well positioned for that because we have this ability to run some of these complex algorithms on the CPU, but we also have the ability to do the heavy lifting in the highly parallelizable infrastructure that the GPU provides.
Another element of the hardware and software collaboration is in terms of the quantization that you might do for inference time on a model where maybe natively it wants to be floating point 16-bit, but you want to quantize it down for better speed or the ability to run on less capable hardware. I'm wondering how that hardware element factors into the ways that you think about the software layer for either enabling the work of doing that quantization or being able to improve the efficiency of the compute maybe without having to quantize.
Yeah, the way I would look at quantization is it almost gets to an art form because you have so many hyperparameters to tweak, right? But you want to be able to preserve the quality of service of like, is your model outputting the same thing? And some of it gets very subjective, right? Like I've personally seen deployments where the customer's like, as long as the end user doesn't notice what's going on, you're good. You can quantize it, right? So then we have some additional aggressive mechanisms to shrink from like float 16 to float 8 or even lower, right? Like our next generation hardware will have FP4 support, which is 4-bit support. The computation itself is in 4 bits, right? And that increasingly gets like your numerical range is just 4 bits. And just a few years ago, we were doing everything in FP32. From 32 to 4 bits is like the industry has shifted drastically. So we still have some of those SLAs to deliver to and make sure that the model doesn't lose its accuracy. But that's an interesting area of both research and production, right? As an example, like there was a time pre-LLMs that Int4 was considered like info was for a time it was considered it's going to come. People put it in hardware. I think A100 had it or something, and then H100s removed it because there's no use for info, and then suddenly info just became a thing, right? And LLM showed up, and now info or FP4 is like it's real. So there was a cycle of like, oh, quantization below a particular size is not going to work out, and then similar to DeepSeek, right? DeepSeek showed the first actual training with FP8 with all the tricks they did to get FP8 training to work. So it's a very exciting space and one that we at AMD heavily invested.
And then for the people who are in the process of designing their AI stack, they're figuring out what to invest in, what are the software components that they want to rely on. How does the fact that ROCm is open source versus the proprietary nature of CUDA factor into the ways that they're thinking about platform risk and the ability to own more of the end-to-end capabilities of the system?
I think the important thing about AI capabilities are unlocked in a way that different parts of the system like factor into different parts of how what gets unlocked, right? Like, and let me give you an example. So, for example, AMD hardware or Instinct hardware has more than 50% memory capacity and memory bandwidth, right? And so what this allows us to do is that we can actually decode LLM tokens very fast because it's all bandwidth limited. But then there are cases where you have a first time to token, which is like how long does it take to react first, right? So it's a balance of like how do you get enough of this so that you don't degrade your SLA, but then you want to run fast and generate like an entire story fast. But that requires like balancing not just on not just a computational optimization. It could be like power. It could be various other end-to-end systems that we have to orchestrate. And the software to manage that gets very interesting and complicated. And we have to build that to be able to unlock this level of like customization.
And then digging a bit more into the software stack that you're building, ROCm is the key element of that, but there are also a few other layers available, such as the Hipify ability for being able to translate CUDA into more portable C++, And I'm wondering if you can just give an overview about all of the components that exist in the ROCm stack specifically and some of the surrounding ecosystem that builds on top of it.
So we approach this with like a multi-layered approach. One is there are customers that have invested in like NVIDIA and down to PTech level code, right? They've invested very heavily. So for them, we have this Hipify tool, which takes their CUDA code and converts it to portable HIP code. And portable HIP code can in turn be compiled back onto NVIDIA code or systems or onto AMD systems, right? It literally is making it portable. But then there's a layer on top of it, which is like Triton, which provides you the ability to like start from Python and then target AMD or NVIDIA or other GPU platforms. And Triton provides you this easy to use abstracted GPU programming interface that allows for like very easy ramp up to get to like almost good performance and then let the compiler do the rest. So we invest both in the first layer, which is, hey, you got some CUDA code and PTech code, we'll help you translate it. That's Hipify. But then if you're coming in new Bluefield or Greenfield deployments, you kind of come in and you have Triton as the way that you kind of have to implement it, because then it gives you the portability and it's a modern kernel programming language that you could use to target either of AMD or NVIDIA.
And then one of the main reasons for releasing software as open source is to allow for other participants in the ecosystem to contribute back to it, take it, fork it, customize it. And AMD is definitely the main driving force behind ROCm, given that it is targeting AMD hardware primarily. And I'm curious, what are the incentives that exist in the ecosystem for other people to want to contribute back to that and customize it?
Yeah, very good question. So what we've done in the past few months is actually make ROCm more accessible. It's not just open source it's not just like, hey, it's something out there and we'll do whatever we want and we'll update it and throw the source code over. So we truly are moving to an open development model. And so what this provides is the ability for anyone to take all of the source code and modify it and do what they want to. For example, AMD's Strix Halo laptops are very popular laptops and desktops because you get 128 gigs of RAM that can be used between your CPU and GPU. And the ROCm builds were getting more and more robust with a solid CI and the ability to build. And the community was able to add Windows support on ROCm devices, which we were slowly working towards, but the community was able to pick up and accelerate that pace. And so now, as of yesterday, we have someone who just tweeted about like how they are running PyTorch on Windows without WSL on ROCm, right? Like that's the power of the open source ecosystem. And we don't want to hold up innovation and speed. And that is why we think, we'll run the race faster as we speed up, because it's just going to be more people scratching their itch, doing the thing that they want to do, but then it lifts all boats and then all boats move faster, right?
Another aspect of the ecosystem for hardware for AI is that there are different load patterns, different requirements around the different stages of the life cycle, from pre-training to post-training to fine-tuning to just running it as inference. And for different consumers at different stages of that life cycle, they have a different relationship to the underlying hardware, where as an end user who is just using an API for AI inference, I don't necessarily care what the actual hardware is under the covers there. I just care that I get some reasonable response times. Whereas if I'm somebody who is investing a lot into pre-training a substantial model, I'm going to be much more focused on what the hardware is, the software stack on top of it, et cetera. And then in the middle, if I'm a company that's running my own VLLM or SGLang instance for being able to customize my inference, I'm going to maybe be somewhere in the middle where I've got a cloud provider and I just say, just give me some GPUs. And I'm wondering how you think about the ways that you're interacting with people along those different stages of that life cycle.
That's a very good question, and you like segregated the market. The thing for AMD is like we plan to go through with every one of those three users, right? So there'll be different routes to market, but we'll get to the end user, and those end users would, if they consume from an API, it's just going to be DeepSeek R1, the fastest and the most throughput is on MI300 today. And so for the end user, they're just going to see their tokens, served per dollar or the cost per token to be low, and it's just value provided with that, right? And so similarly, we're building out how you do distributed inference, so you can even get even further economies of scale by disaggregating, prefill, decode, etc. But then on the other side, we also help. Hey, you want GPU as a service, and then you need an entire stack on top. We provide the reference architecture of that stack so that it's not like, hey, we give you a GPU and we don't know what to do on top of it. So you got to take all the pieces, put them together, tie it in together, and then move it forward. And then the third one is obviously it's on-prem or they have their own clusters, and they know exactly what layer of the software they need, and they'll replace something. They'll have their own Kubernetes deployment layer. They'll have their own training framework that they've modified from Megatron LM or JAX. They're like the super sophisticated frontier labs, right? And I think that if you look at like the top 10 customers, those would be, will fall in that bucket. And a vast majority of them do have AMD deployments. So it is, it's a growing phase where I think we will, it's just like what we did with Epic, right? Like it's just a matter of time before it's an option. And then the others would be TCO advantage by just saying, hey, yeah, if I serve on MI300, I get more performance and it costs me less. So I'm just going to serve, they'd request an MI300 backend. So that's how, I look at it.
Another element to the software investment for powering particularly these very numeric and parallelizable workloads that are epitomized by these large language models is that there has been a lot of effort going into now trying to reduce the computational load for training and for inference, either through different attention mechanisms or the work that's going on with mixture of experts, and then also some of the newer architectural patterns where transformers are trying to move beyond transformers. I'm thinking in particular Mamba or the diffusion based models or the work that the liquid networks folks are doing. And I'm wondering how that feeds back into the ways that you're thinking about the software stack that is able to improve the efficiency or the capabilities of these different model architectures and these different compute patterns that get translated to the underlying hardware.
Yeah, that's a very good question. The way I look at it is it's like layered cheese, right? So the you just have to invest in each layer to be robust and solid, so that when there's a switch from transformers to Mamba or SSMs or other architectures, it's not a question of if, it's a question of when. When that happens, we already have the underlying infrastructure and the core compute, disaggregation and how you network all of these compute, those libraries and infrastructure is robust enough for a switch at the top level, right? Like at the modeling level. But then on top, again, there'll be another level of like, bringing it back to an API, right? Like in the end, the last mile for the end user is going to be an API. And that's going to be, something like a OpenAI like API for LLMs, but that can also change and evolve over time. But there's a fan out in between the very low levels of the software stack, and then as you get to the middle layer, there are paths of innovation that will we explore. And I can tell you at AMD, and from my view, all of those facts that you talked about, we are very well invested in, and we bring it up there. So I think the way I approach it is, how do you be prepared to react, and how fast can you react? That's going to be the currency for being relevant in this fast moving AI world.
And then the other potential target for an end user is for people who want to be able to do their own local inference on a laptop using these open models, and they want to be able to do it reasonably affordably without having to run their own power plant to be able to power the cards. And I'm wondering how you're thinking about that consumer grade aspect of AI and the ways that people are able to run them on their local laptops, on their desktop machines, or on edge compute for being able to bring this into more of a personalized mode without having to necessarily be a AI researcher and understand all of the things that they need to know to be able to quantize the models and fine tune them to be able to run effectively on the silicon that they have in whatever device they might have ready to hand.
Yeah, so AMD has a very pervasive AI story, right? Like we go all the way embedded, automotive, like autopilot devices, and then laptops, like the Strix Halo laptop that I was talking about. It has like 50 TOPS of compute on an NPU. So NPU, think of it as like when you need efficiency, when you can trade efficiency to programmability, you go for an NPU. When you want the programmability, you use an iGPU. But then you also have a CPU, which is your fallback, right? And all of those pieces of silicon are AMD built and in a laptop form factor. So in fact, I have my Strix Halo laptop over here, and it's got all of that tied together and an open source software stack that runs everything on that is open source, right? So it's not like, hey, install CUDA 5.8 something, right? If you want to build it, you can take it, build it, and tinker with it, right? So it gives you that ability, and we see incredible innovation with the likes of Llama CPP and Olama and the client side of inferencing, where they go in and kind of make these big innovations, and especially in quantization, right? So we're going back to your original point, like Llama CPP was the first one to make like Q8, Q6, Q5, and you can change only a few tensors to be this, and your perplexity looks okay. So it almost gave you like per tensor level fidelity to be like, okay, this model can now run on this, and then there's a big lever for how much VRAM you have. So they map VRAM to this, and they find a sweet spot of a model that can run locally. And I think increasingly we're going to see even algorithmic innovations where you have like a actor critic model or student teacher models. And I think if I remember right, Llama 4 Behemoth was also used in a similar way, right? Like where you use the very large model to be the teacher, and then your small model distills and learns from the teacher, but it's a smaller model. So there are like innovations happening at each layer of the cheese, right? It's that at the hardware level, quantization level, at the modeling level, and put all of them together. I think increasingly you'll see a lot of local AI.
And in the work that you're doing of building this software ecosystem on top of the core silicon capabilities, the work that you're doing to make it open and accessible and flexible, what are some of the most interesting or innovative or unexpected ways that you're seeing that combination of AMD hardware and the ROCm ecosystem applied?
Innovative ways that we are seeing that we hadn't envisioned that people are using it in. So the cool things I've seen, like I've seen an AMD GPU, like a normal PCIe card, stuck on like a RISC-V CPU, and they built a little thing with a AMD GPU that wasn't even designed to run on a host with RISC-V. But given it's open, they could actually port the driver and get it to work, and they actually just have a solid graphics card now running on a completely new CPU architecture because of the open, like architecture that we have, open ecosystem that we have at AMD. I've also seen some the mention of like Windows portability, right? Like the community did a lot of the work to get Windows portability of ROCm, and now we have ROCm that just works on Windows. We do have the likes of like TinyGrad, where they're building a lot of AMD cards together to put together a cost-efficient petaflop machine. That's also very exciting. Yeah, just a lot of innovation at the application space with the local AI, where you can run your like coding assistant on your laptop and it's answering questions in real time. That's really cool to see. Yeah, things like that are, and there's more coming every day. You just have to keep up with it.
And in terms of your own experience of working in this ecosystem, working very closely with the AMD hardware units and the end users and the software contributors, what are some of the most interesting or unexpected or challenging lessons that you've learned in the process?
I think as ROCm and AMD software has a long history, right, and it has evolved, and so there's a perception hurdle that we had to get over. I literally am on X or Twitter listening for anyone complaining on like about AMD software or ROCm software. This is not working or that's not working, and I try to navigate and try to get them the support that they need. So it requires a little bit of re-educating and asking folks that may have formed an opinion on AMD software to see where we are now. And that's always a little bit of a thing, right? Because you've had an experience that was subpar at some point, but now you're asking for your second chance. Navigating that is interesting. And then just communicating what we all are doing. Like, do people know about ROCm? Unlikely, right? Do people know what's the best GPU to serve DeepSeek on? Unlikely, but that should be straightforward. It should be like the fastest way to serve DeepSeek is on AMD. That's like a fact, and that fact is just about how we market that and get that out, right? So hopefully we'll work on that and help people kind of like realize the value of what they can get with AMD hardware and software.
And the talking about the speed of inference too just made me think about another element of the serving piece is that oftentimes you want to be able to run multiple copies of the model if you're trying to do it for a number of different users simultaneously, which then brings in questions around being able to split the models across multiple GPU instances or being able to manage coordination of multiple GPU instances to pool together in a single batch of compute. And obviously, AMD is being used in various supercompute ecosystems. I'm wondering how you're thinking about that ease of use of being able to pool together multiple hardware units to be able to manage this inference serving or for training.
Very good question, but I would actually take it a level lower. AMD is the industry leader in chiplet design, right? Our competition is going to do that in a year or two, right? Where they actually get chiplets. The MI300 today and MI250s, and like for few generations, we've built multiple chips that are in one big package. And so what that provides is we're already doing that at a chip level. Today's MI300 has something called the CPX mode, which gives you 8 levels of 8 chips with 24 gigs of HBM each that you can actually partition as an independent GPU, and you can have NUMA locality to the CPU. It is actually like physically you turn off the connections and you have a GPU, right? And so what that provides is the ability to build from like fundamental building blocks, even at the SoC level. And then that gets up to the GPU level and you have 8 GPUs at a UBB level. And then you get to a multi-node rack level, and then from a rack to a cluster level. And each of that kind of like inherently, if you build it from a first principles of how you do communication and compute, you start building a very, very robust, software architecture. And there are challenges in how AMD had done it in the past that we are kind of like, have evolved over time. But today, going back to chiplet designs, you could actually partition each one of these GPUs, and we have instances of VLLM or SGLang running on each one. So you have 8 instances of VLLM serving Llama 8B, for example, and it's fully isolated, right? So you get 8x the throughput just by parallelizing, at a chiplet level. So it's very exciting for computer scientists and for folks that want to like just deal with operating system principles like resources and allocation and how you're efficiently using compute communication, right? So AMD is built for that, which is what I'd say. If you're in that space, we're obviously hiring. Drop me a note, and there's a lot of fun activities to do and engineering to do with that.
And given all of the conversation we've had around the benefits of AMD hardware, the ROCm ecosystem, what are the cases where one or the other or both are the wrong choice?
If there is a wrong choice, let me know. I'll make it a right choice. But I think there are cases where I wouldn't say see the ROCm software should become invisible. It should just become magic, right? It should just be hey, there's hardware resources and there are APIs to do something, right? And then you can do something on top. And what that something is like VLLM serving. And then on top of it, you build something else, right? So ROCm as an interface should just disappear. Like people should not have to think about it as a moat because it's open source, and it should not be thought about as like buggy because it doesn't exist in your. It's just there. It's like ambient enablement of the compute and networking, right? And then you get to the GPUs itself. GPUs themselves have their pluses and minuses, right? So you've always had, and this goes back to classic computer science trade-offs of like, hey, do you need programmability or do you need specificity, right? So do you go general purpose GPU, general purpose CPU, or do you go for ASICs? You always have that, trade-off, and the rate of pace of innovation of things keep most of that in like GPUs is the sweet spot where that innovation will happen for the foreseeable future. And then, yes, if you want to serve some specific customer with something, you want to build an ASIC, it takes you 2 years, and you don't care that 2 years from now, you still want to be serving OPT 1.7 175B. Fine, build an ASIC that serves OPT 175B, but it may be irrelevant. So then you try to make that a little more programmable. Then you're like, oh, but it's a little programmable, but it's not fully programmable. Then it's a trade-off. Then you're like, okay, you're not an ASIC, you're not here, but you're going to be halfway there. And then, the halfway point is always like there are one-off benchmarks. You look at some of these ASIC vendors, they're like, oh, we serve Llama 20x faster. But if you go read the fine print, it's like, yeah, Llama has to be only 2K context length, while GPUs are serving like 1 million context length. So you're saying all your requests will have to fit into like a little envelope, and then we'll serve these envelopes very fast. Sure, if that's what is needed for your customer, great. But I think in general, like it's classic general purpose programmability, and I think there's a market for that, and that's a huge market. It'll be good for that, but that doesn't mean we don't do semi-custom or custom, right? Like all of the big consoles use AMD, and so we are there in the entire journey, and whether it's on your hardware side or software side for AI.
As you continue to invest in the future direction and capabilities of the hardware layer and the software support to go along with that, and the ways that the AI ecosystem is continuing to stretch and strain those software components, what are the things you have planned for the near to medium term for your own work?
Near to medium term, I'd like to make ROCm quality is really high on my mind. It should just be like nobody should complain about ROCm quality. That's number one. It should be easily hackable and usable. It should be like the hobbyists and developers need to end up there. Because why? Because it's easy to use and I can just hack it. If something doesn't work, I'll go in and go fix it, right? Like that should be the mentality. But then we have developers with the developer outreach where we want to go and get everyone to taste and explore and feel, oh, this is what it feels like to use ROCm, and then go use that. So those are the three that I focus on. But then obviously on the other side, I want to make sure customers are successful, right? So that's where rubber meets the road. If the customer is not successful, then that's not good either.
Are there any other aspects of the ROCm ecosystem, the work that you're doing at AMD, or the role of AMD in this broader AI ecosystem that we didn't discuss yet that you'd like to cover before we close out the show?
I think this is a good time to be in this space, and we're at an inflection point of both hardware innovation, software innovation, how we touch people, and what it means for like humanity at the top level, right? Like because increasingly you're going to be AI assisted in some form, right? Like composing an email to do something somewhere is just you talking to your device or your chatbot to say, hey, write this up for me, and it's going to give you most of the framework, and then you're going to go and add bells and whistles, right? So it's going to creep up on you in a way that is going to be profound, and 5-10 years from now people would assume that's how things are done, right? So otherwise, from an AMD standpoint, hardware and software, it's just one step in front of the other, and we're just going to keep executing and be there for this transition in this industry.
Well, for anybody who wants to get in touch with you and follow along with the work that you and your team are doing, I'll have you add your preferred contact information to the show notes. And as the final question, I'd like to get your perspective on what you see as being the biggest gaps in the tooling, technology, or human training that's available for AI systems today.
I think it's a combination of all of them, right? And I think it will go down in like when we look back after this transition phase, and this can be like 20 years, right? It can be over a longer arc of time. It's going to require a combination of all three of them. Like people will have to retrain to be able to use a new way of communication, right? It's like emails, but it's assisted and it already knows what the other person's asked, and you've already got a draft that's composed saying this, or this, right? And your job is like swipe left, swipe right on like, okay, this draft or that draft. And so it may distill it down to that. So, but then when it comes back to the fundamentals of like compute and power to power that compute and AI services, it's going to be another layer of like learnings or of and development of new tools. The way I look at AI is it's like electricity, and now we're like, oh, here's electricity, go do what you have to do. And there's a whole wide world of like what we've explored and done with electricity. And we're the same, like, we're just in the start of the AI era where we're like, oh, we got AI, here are frontier models that can do this. And then like, is it Cursor and whatever Windsurf for coding? Is it the next version of Canva to do AI based something? How is Salesforce.com going to be working in an AI agentic world, right? Like, and that's up for someone to go innovate and figure it out. So it's very exciting and to be in this space.
Absolutely. Well, thank you very much for all of the time and effort you're putting into broadening the availability for people to expand the set of hardware that they're operating on and the ability to tinker with it and understand more about the end-to-end stack. It's definitely a very interesting problem space. It's great to see that AMD is being so open with their work there. So appreciate the time and energy that you and your team are putting into that. And I hope you enjoy the rest of your day.
Thank you for having me, Tobias. Thank you.
Thank you for listening, and don't forget to check out our other shows, the Data Engineering Podcast, which covers the latest in modern data management, and Podcast.init, which covers the Python language, its community, and the innovative ways it is being used. You can visit the site at themachinelearningpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts at themachinelearningpodcast.com with your story. To help other people find the show, please leave a review on Apple Podcasts and tell your friends and coworkers.